All right, kiddos, time for the very last thing in Power Series. Today we got to talk about error. So how far off are our approximations? Remembering that a Power Series is a polynomial approximation for a more complicated curve. So if we start with this request here to write a fourth degree Taylor polynomial for that function. Oh, that function's missing natural log, the natural log of that. That's fine, we can do that because that's in our memory. So we know that the natural log of the absolute value of x plus 1 from my memory, I got x. It is an alternating series. Oops. No factorials. And I need to go all the way until x to the fourth because it wants a fourth degree. So there, I did it. That is not the exact same curve. That's why I have the squiggle equal signs. And now let's use it. So using this, the next part of our question is we're going to use it to approximate the natural log of 3/2. Well, okay, so if this is a polynomial approximation for natural log of x plus 1, and I need the natural log of 3/2, then I'm going to set x equal to 1/2. So we are going to use the polynomial that we wrote, substituting in 1/2 everywhere that there's an x. So we get 1/2 minus, we get 1/2 squared over 2, 1/2 cubed over 3, etc. All the way. And this would be a pretty good approximation for the natural log of 3/2. If I type this into my calculator very carefully, I get 0.401. Okay, that was fun. But now the question is, how good of an approximation is it? I feel like it should be pretty good because I've got 4 terms. That's a pretty complicated polynomial that's being used to approximate this curve. If it was only a couple terms, it probably wouldn't be as good. But here's how we're going to find error. Now, what we're finding is not the exact error. So listen to this. If we were finding the exact error for our approximation, then it wouldn't be an approximation anymore. If I knew exactly how far off I was, then I would know the exact answer, and it's not an approximation anymore. So it's not the error that we're finding, it's the maximum error. It's how far off could we possibly be. So it's not a for sure thing. So for this one, to find maximum error, you have 2 choices. The first one, if you were dealing with an alternating series, then your max error is equal to the absolute value, because I don't care about positive or negative, the absolute value of your first neglected term. If not alternating, then we do this error called, it's called Lagrange error. Sometimes it's called remainder. So those 2 words are used interchangeably here. Okay, so this polynomial that we have, this Taylor series that we have, is alternating. Hooray! That means I'm going to use this to find our maximum error. So our max error for this series is going to be the next term that I didn't write. Well, I got to a 4th degree, so that means our max error must be x to the 5th over 5, evaluated at x equals 1/2. So this is 1/2 to the 5th over 5. And if you type, you get 0.00625. So that's the maximum we could be off in that approximation. It's actually not super great because this means I only have 1 decimal accuracy. Like I'm only accurate to the tenths, because if I stop here, then this 6 would round this up to a 1. And so I'm not necessarily accurate to 100th place. So the only thing I know for sure is that it's 0.4. But that might not be a 0. I don't know this value for sure. So, all right, if they wanted more accurate, we'd give them more terms. No big deal. That's how we find error for an alternating series. It's just the next term that you didn't write. So let's talk about if it's not alternating. And we're going to do it inside of a question. So let's use a third degree Taylor to approximate the square root of e. Okay, let's think of this as e to the 1/2, and let's start building a polynomial. I have a polynomial in my brain for e to the x. I hope you do too, or it's getting there soon. It looks like this. One more. I'm stopping here because it wants third degree, so I'm stopping at third degree. If they want me to use this to approximate e to the 1/2, I'm just going to go replace all my x's with 1/2. So this is 1 plus 1/2 plus 1/2 squared over 2 and 1/2 cubed over 3. And if I type very carefully, I get 1.646. Okay, that's great. I hope it's good. Let's find out. Here's how you do Lagrange error. It's going to look really scary, so I'm going to write it in silence so that you can brood over how terrible this looks. R is for remainder. Are you terrified? You might be. But then you're going to look at it a little bit closer. And I hope that as you look at it closer, it becomes more familiar to you, because this is just a Taylor term. So if we stopped at a third degree, because that's where they told me to, then this Taylor term is for the next one, because I've got n plus 1s everywhere. So the only piece that's coming out of left field that I'm very confused about is z. Z is some value between a, or I use c with you guys, between c and x, and you get to pick any z value you want between c and x. And the way you know how to pick is you pick z so that that part of your Taylor term, so your derivative, your n plus 1 derivative at z, is maximized. Remember, our goal is to find maximum error, not exact error. So my goal is to make this as big as it possibly can be within this interval. So that doesn't always necessarily mean that you're picking the biggest value. Sometimes you want to pick the smallest value. It just depends on where it gets plugged in and what the derivative is. So let's talk about what c and x are. So c is, this is your center, right? Your home base. X is where you're approximating. So it's the value you're approximating at. All right, so if I apply this to this e to the 1/2 question above, I stopped at a third degree, means that for error, for our maximum error, oh, I guess I should say again, it's also absolute value, because it's not negative, it's a distance. But our max error is going to be our next derivative at z. That's the part I don't really know about. And then what, x minus c to the 4 over 4 factorial. So instead of stopping at a third degree, I go all the way to the 4th. I just realized I changed letters on you here again. This should be a C. Sorry, C for center. I have done A every other year. My fault. Okay, and then I know that Z is trapped between home base, which is 0, and 1/2, which is where we're trying to approximate. So if I'm trying to make this as big as it can possibly be, e to the 0 is 1. Square root of e is bigger than 1. That's all I need. So this is the choice I'm going to make that derivative as big as it can possibly be. So this is e to the 1/2. This is 1/2 to the 4th. This is 4 factorial. And I'm going to type, and I'm going to get 0.00429. So this one must be a fairly good approximation. I at least have 2 decimal place accuracy, as opposed to the last one where I only had 1. All right, kiddos, that was a lot. Go do some homework because this is strange and hard and new. And see you later.